to the computer. Hi, everybody. This is the first of probably 3 short videos covering section 5.1 in the text. Since this is the first section in chapter 5, I want to say a couple things about chapter 5 and so sort of the big picture of what we're trying to do in this chapter. And then I'm going to shift over to my document camera and start using the document camera kind of like the whiteboard that we'd have normally in the classroom. So first off, chapter 5 fundamentally is about developing techniques for proving trigonometric identities. And we'll use these techniques to develop some important results in section 5.3, 4, and 5. But those are kind of a little bit down the way. For the time being, section 5.1 is really about recalling some of those critical skills and in some sense doing problems that we've done previously, but in a new context and in a way that will reinforce some of that proof skill. So like I said, I'm going to shift over to my document camera here, and hopefully everything's kind of in focus. It may take just a couple seconds for that to shift over. I think I have to get rid of my virtual background so you can actually see it. There we are. Okay. Well, everybody's getting used to this new technology, folks. Okay. So just since this is the first video, I'm just going to let everybody know that I will make the sheets that I use during this presentation. I will make these available to everybody on Blackboard so that you will have those notes. It may be better than trying to scribble everything down if you just kind of pay attention to the information that I'm giving them in addition to this. So this is section 5.1, and 5.1 is entirely related to what are called the so-called fundamental identities and some minor applications of these. Okay, so there are, for our purposes, there are 5 sets of so-called fundamental identities that we will use repeatedly throughout the chapter to prove other identities. There are, as I've alluded to several times, there's an infinite number of identities, or probably maybe not quite an infinite number, but anyways, there's quite a few, and most of them don't have a whole lot of use. They more are just useful practice, because as you may encounter in a calculus class, it may be useful to take an expression and transform it into something else that's a little bit easier to work with for one reason or another. Anyway, so let's just dive right in. The first, and you've seen most of these in chapter 1 and 2, and then some that actually come a little bit later. But the first couple should look very familiar. So the first set of identities are what are called the reciprocal identities. And I'm going to start abbreviating some of this stuff because we're going to end up writing it a bunch. I'll usually abbreviate it as, when we're performing a proof, it's usually a good practice to put the rationale to the right of each step in the equation or in the proof. When you link ideas by an equal sign, you generally need some kind of justification. If you do more formal proofs, there tends to be a lot more words than actual equations. So anyways, this is just kind of a foray into that realm. So the reciprocal equations are related to the identities that are reciprocals to each other. And as an example, sine of x is equal to 1 over cosecant of x. Similarly, cosecant of x is equal to 1 over sine of x. And this is not unfamiliar to us. There are 6 of these total identities. There is one involving cosine, so cosine of x is equal to 1 over secant of x, and similarly, secant of x is equal to 1 over cosine of x. Finally, we have tangent of x equal to 1 over cotangent of x, and cotangent of x equal to 1 over tangent of x. Okay, so these, like I said, these are not unfamiliar, but I want to just point some things out that what's critical about these particular identities, and when we get into the habit of just writing x or theta or whatever with these as if that's not really important. But what is critical here is to recognize two things. One, that the argument, when we see an identity like this, it doesn't necessarily have to be x. It just has to be the same thing. This could very easily be, 2 theta plus, you could have something along the lines of sine of 2 theta plus pi over 2. Well, by this identity here, that will be equal to 1 over cosecant of 2 theta plus pi over 2. So it doesn't have to just be x. I mean, what's critical is that they are the same. Also, and this is kind of a bigger picture idea, is that it's important to recognize that these identities only hold when the argument is in the domain of all the functions in the equation. So as an example, we know that 0 is in the domain of sine. In fact, any angle is in the domain of sine. And sine of 0 is 0. But that does not necessarily mean that the right-hand side somehow has any meaning. Because as you know, cosecant of 0, well, 0 is not in the domain of cosecant. That becomes an undefined quantity. And so 1 over an undefined quantity doesn't suddenly become defined. So the key to any of these, sort of the underlying hypothesis of any of these identities, is that the argument is actually in the domain of all functions involved. Okay, as long as that's not a big point, because it doesn't tend to happen in this course, but it may be something that you could see later on. Okay, so those are the reciprocal identities. Then there's a relatively small class of identities called the quotient identities. And again, we've already seen these, but now we're sort of formally giving them some names and maybe doing a little bit of analysis of them. So these can actually be proven from these reciprocal identities, or maybe even the definition of the trigonometric functions themselves. So tangent of x is equal to sine of x over cosine of x. Now again, now x has to be in the domain of all three of these functions, which again, the domain of sine and cosine, well, all angles are in the domain of sine and cosine, but we know that tangent is undefined for certain values. And so this, obviously, in that particular case, the identity would not hold. Now, remember, that's when it turns out that tangent is undefined at exactly the same places where cosine is equal to 0, and you have division by 0, which is what really causes the problem. Anyways, so these are usually paired up with their with the secant version. So sine of x over cosine of x is itself equal to secant of x over cosecant of x. And now we have actually 4 functions involved, all 4 of which have to be, for any particular argument, they have to be defined. Otherwise, this equality is not going to hold. Okay. There is another set of these that involve, instead of tangent, they involve cotangent. They can actually be proven from the reciprocal identities and this the first set of quotient identities, but we'll call them a fundamental identity anyways. So remember, because cotangent is a reciprocal function of tangent, we're just going to exchange numerators and denominators and come up with some very similar looking identities. So here we have cotangent of x is equal to cosine of x over sine of x, which happens to also be equal to cosecant of x over secant of x. Now, one thing I will note is that there is a for whatever reason, because once you see this identity, there's this tendency of students to want to make some kind of a relatively simple relationship between sine and secant or cosine and cosecant. It really does not work like that. We will see as we go a little bit further in the chapter, we will see situations where we can make say sine in terms of one of these others, and they are not simple, right? They generally have, some radicals in them, maybe even some ratios, and generally speaking, there is not a simple way to write any function in terms of another, other than the reciprocal functions. Okay, anyway, so I think I'm out of space here on this page. Let's move on to page 2 here. So again, this is section 5.1. And now this will be page 2. I'll probably keep it running total for all the pages I create for section 5.1. And that's what you'll see on Blackboard. But I think I've practiced this enough times that I think I'm only going to end up using 2 pages for this first piece. Okay, so the next set of fundamental identities is the so-called, and these are really important, these so-called Pythagorean identities. And recall, we proved these almost at the very beginning. It may have been section 1.2 or possibly 1.3, maybe 1.3. But they can be proven directly from the definitions of these trigonometric functions and the distance function. Anyways, we also saw them fairly recently with in section 3.3 with the unit circle. Recall that we looked at certain segments that were constructed at different locations throughout the unit circle, and these so-called Pythagorean identities popped out as a natural consequence of being able to create geometrically right angles using the unit circle. Anyways, so you've seen them before. Sine squared of x plus cosine squared of x is equal to 1. This is the so-called first Pythagorean identity. The second one is tangent squared of x plus 1 equal to secant squared of x. And finally, cotangent squared of x plus 1 equal to cosecant squared of x. Now, I will tell you that it has been my experience that for some very strange reason, and I want to be clear, this is really not true. There is this mistaken assumption that because the Pythagorean identity holds, I don't know, maybe it's a holdover from what people try to do in intermediate algebra when they've got these squared terms. It's like they think that because if you take the square root of both sides, you're going to end up with something very simple, something that. And this is false, and I want to be careful about that. False. Just because this say for example, this first Pythagorean identity is true, false, that does not mean that sine of x plus cosine of x is equal to 1. Okay, and I put that not equal to specifically. Now that's not to. And I'm just going to be careful here and say in general, because there are certainly values of x for which this equality holds, but it's not true for all values of x or all values of the argument. And so that's really what you're trying to create a distinction. In chapter 6, we will solve equations like this, where we will find exactly which angles it holds true for. But it's not true for all angles. And that's the difference between, say, an identity and an equation. Okay, so moving on, we have the so-called a couple of identities, a couple of classes of identities that aren't super useful. We use them a couple of different places, but they get relegated kind of pretty after we get to the sum and difference identities. They become kind of irrelevant because they're kind of special cases of it. But we've talked about these before. These are the so-called co-function identities. I don't have a real good abbreviation for cofunction. Usually I will just spell it all the way out, cofunct. This has to do with that we had said previously that the cofunction of a complementary angle is equal to the function of the angle, or something along those lines. But it basically gives you some insight as to where the names of the trigonometrics come from, right? The names of the trigonometric functions. So cosine and sine, how are they related? Well, it so happens that if you take the sine of an angle, that happens to be the cosine of the complementary angle, right? And so we're going to formalize those. I'm going to use radians because we've probably seen them with degrees enough to puke, but reinforcing the radian concept is kind of critical. So sine of pi over 2 minus x happens to be equal to cosine of x. That's one of them. And it just so happens that cosine of pi over 2 minus x is equal to sine of x. So they kind of go both ways. There were 3 sets of these, one involving sine and cosine, one involving tangent, cotangent, one involving secant and cosecant. And as I said, you've seen these before, so kind of rush through them a little bit here. So the tangent of pi over 2 minus x is equal to cotangent of x. Similarly, cotangent of pi over 2 minus x is equal to tangent of x. And now the ones involving secant and cosecant. Secant of pi over 2 minus x is equal to cosecant of x. Similarly, cosecant of pi over 2 minus x is equal to secant of x. Okay, and this is sort of the first set of identities where we start manipulating the argument. Prior to this, they've all just been x, just some sort of generic placeholder for the argument. But now we're starting to manipulate inside the argument in some way. And as we progress through chapter 2, we'll come up with more and more complex kinds of manipulations of the argument, not just the functions themselves, but also the argument in many cases. Okay, and then the last group of fundamental identities are ones that we've only seen relatively recently in chapter 4, and they're based on some geometric or some graphical ideas that you'll recall from college algebra. We said, well, if a function is symmetric with respect to the y-axis or the x-axis or the origin, it has certain properties. Well, we use different terms. We call them even and odd functions, but they have the same effect, that they create an identity that involves the insertion or the removal of a negative sign into or out of the argument. Recall this with odd functions, so-called symmetric with respect to the origin, odd functions, that the negative sign could pop in or out of the argument. Whereas with an even function, the so-called symmetric with respect to the y-axis function, the negative sign can be ignored. You can arbitrarily insert a negative sign and it doesn't affect anything else. So to kind of spell them out, the so-called symmetry identities, and we won't use these too often, but for completeness, we'll put them in there. So sine of a negative argument happens to be equal to negative sine of the non-negative argument. Now, you got to be a little careful with this because x could actually be a negative number, right? But most of the time, you're using this to simplify the argument by reflecting the graph in some way. Although it is possible you might want to work the other way. Now recall we said with functions, if the function is, say, odd, then its reciprocal function has the exact same characteristics. It will also be odd. So almost for free, we get one that's related to the reciprocal function, that is cosecant of negative x equal to negative cosecant of x. And then our first odd function is cosine. Cosine of negative x is just simply equal to cosine of x, which is nice. I mean, it's like we can just ignore negative signs. We can bring them in, we can take them out, and it doesn't really affect anything else. Similarly, secant is the reciprocal of cosine, and so it has the same sort of behavior. So the secant of a negative argument is actually equal just to the secant of the same positive argument. That negative sign is irrelevant. Finally, we have tangent. Tangent is, again, an odd function, and so the negative sign has an effect. You can bring it out, so to speak. This is kind of a nice property because if there was anything else in here, like a 2 or something like that, you can't just pull those out. But the signs, the SIGNs, actually typically have these fairly nice properties. Okay, anyways, and then finally we have one for the reciprocal function of tangent, which is cotangent. So cotangent of a negative x is equal to negative cotangent of x. Sorry about that, got missed just a little bit. Okay, so what are we going to do with these? What I think is critical at this point is to be able to remember, and that may require direct memorization, remembering all of these identities. Now, I know there's a lot. I mean, if you look back at them, let's see, we've got 6, 12, 18, 24, 27 different identities, but we've been building up all semester to get to the point where we already kind of know these. These are going to be the basis for proving additional identities. And there aren't a whole lot more that are really important. So, it's this exercise that we're going to engage in. Okay, so this is the end of the first probably of 3 short videos for section 5.1, and I will be back with episode. Well, I guess I'm not sure how I'm going to categorize these, but this will be section 5.1.1 probably, and the next video will probably be called 5.1.2. Shocking. Okay, well, that's what I've got, and we'll be seeing you soon.